Okay, so as you remember, we were talking about virtual memory, and hopefully you've done the reading. And I'm going to go through some of these slides to jog your memory. Basically, the key idea in virtual memory is to give the programmer the illusion that you have infinite capacity memory while you really have a small physical memory, so that the programmer doesn't need to worry about managing physical memory. And the programmer can assume they have infinite amount of physical memory, right? And the illusion is provided by the hardware and the software together with a lot of effort, as we will see. And illusion is maintained for each independent process. Each independent process has this illusion separately. And recall that we showed this picture, which showed that this is a physically addressed memory. CPU generates addresses that are physical. Whenever you want to fetch an instruction, the program counter is physical. The load store address is physical. In this case, there are a bunch of issues that we discussed yesterday, which I'm not going to go into. And to solve those issues, basically we added this indirection layer, as opposed to directly addressing the memory from the CPU. We go through a translation table, which is essentially called the page table. And each process has a page table, and you go through that. The CPU generates virtual addresses, and they get mapped to physical addresses this way. And for this to work, this is page-based. You basically divide memory into pages, and the virtual pages get translated to physical frame numbers or physical page numbers. And some of the pages that you address may not be in the physical memory. They may actually reside in the disk because you haven't touched them for a long time, in which case the system brings the page from the disk into the physical memory and change the mapping such that the CPU can directly access the physical memory. And then after that, you can also cache the locations inside the CPU cache. So that's the idea, basically. This way, you're not limited by the size of your physical memory, which could be really small. You're really limited by your virtual address space in the end, which the page table translates into a physical address space. Okay, so you remember all of this, hopefully. So page size is the amount of memory. Memory is divided into pages, and page size is the amount of memory that's transferred from hard disk to DRAM at once. Basically, that's the granularity of the mapping. Address translation determines the physical address from the virtual address, and page table is really the translation table. It's a lookup table that's used to translate the virtual addresses to physical addresses and find where the associated data is. So we covered all of this, and we covered this picture also. This is another picture which doesn't show the page table, but it just shows where the virtual pages map either the hard disk or the physical memory, and this is from your book, chapter 8.4. And the hope is that most accesses hit in physical memory, you go to hard disk only very infrequently. And if most accesses hit in physical memory, that's great, right? That way, the illusion is that you also get the performance of having a very large size physical memory. And existing operating systems and hardware try very hard to ensure that most accesses actually hit in the physical memory, and you don't have to go to the hard disk or SSD as much. Okay, but the programmer doesn't need to worry about it, basically. The programmer assumes that they have the full virtual address space, very large capacity virtual memory. And this is address translation. I showed this also from your book. Basically, you translate a 31-bit address in this case. Existing systems have much bigger virtual addresses, of course, but 31 bits is one example here. You have basically, if this is byte addressable, you have a 2 gigabyte address space, and page size is 2 to the 12, which is 4 kilobytes. And the translation essentially takes the virtual page number and converts it to a physical frame number or physical page number so that it can access the physical memory. And we were doing this example. It's essentially the same example that I showed you previously. Our virtual memory size is 2 gigabytes, which means that it's 2 to 31 bytes. Our physical memory size, we're assuming 128 megabytes, 2 to 27 bytes, and page size is 4 kilobytes. And you can get the virtual address size, physical address size, and the page offset from here, which means also you can get the number of virtual pages and physical pages. So these are easy calculations, as you can see. Virtual page number is 19 bits, physical frame number, physical page number is 15 bits. And this is the mapping for that sort of memory. Basically, this is your physical memory on the left in this case, and your virtual memory on the right. You can see that this is 2 to 31 bytes. And you can see the virtual page number over here. This is page number 0, page number 1, page number 2. And you can see that some of them are mapped in physical memory and some of them are not really mapped in physical memory. So the ones that are not mapped in physical memory, they're either not allocated or they're in the physical disk. Because there is actually an allocation that also happens. Whenever you allocate memory, you allocate virtual memory, and the operating system says, okay, this virtual page is actually allocated, and it's either in disk or in physical memory. And if it's not allocated, it doesn't need to be anywhere, right? Because you're not really touching it in your program. Okay, so these are system-level issues that you will get into in the systems programming course, hopefully. Okay, so how do we translate addresses? This is where we stopped, actually. Basically, page table, as I said, translates the virtual addresses to physical addresses, virtual page number to physical page number. So it has to have an entry for each virtual page. It has to do this mapping. So each page table entry associated with a virtual page number has three things. One is a val bit, whether the virtual page is located in physical disk, physical memory. If not, it must be fetched from the hard disk. Of course, it's a simplistic view. There's also allocated or not allocated that I just told you, but we're not going to go into a lot of detail. And it also has a physical page number. If the page table entry is valid, it must be in physical memory. Then the physical page number specifies where the virtual page is located in physical memory, which physical page. And there are a bunch of other bits in the page table entry that you can see in the backup slides that we're not necessarily going to go into if we don't have time. For example, you need to have replacement policy bits to decide whether what you're going to, which page table entry, which entry you're going to replace potentially, right? Which entry is referenced? We're going to talk about that a little bit. You need to have dirty bits because if you have written to the page, so you fetch the page from disk into memory. And if you write to that page while it's in physical memory, you probably need to write that back into the disk, right? Because you've updated the page. If you have not written to the page while it's in physical memory, you don't need to write it back to the disk. So this is essentially a write-back cache. So you need to have a single bit saying whether you've dirtied or you've written to the page, right? Clearly, you don't want to make it a write-through cache and write every data that you write to physical memory into the disk, because disk latency is very long. We discussed that also. So you need to keep track of this also. And there are a bunch of other things that we will see in a bit, especially when we talk about access protection. But let's talk about translation first. So how do you do the translation? Basically, this is the page table. It needs to exist somewhere. So that's a big issue, actually. We're going to assume that it exists in memory. So there needs to be a beginning of the page table, which is specified by a physical memory address called the page table base register. And this is per process. Every process needs to have a page table base register so that you can figure out the translation of a given virtual address that's referenced by the process. So how do you do that? Let's assume that this is the virtual address that's referenced by the process that is executing. It's 31 bits. It basically obeys what we discussed in the example. It has a 19-bit virtual page number, and this is the page offset. So what do we need to do? Basically, first, we need to index the page table using the virtual page number. In this case, virtual page number is 2, and this is the page table base register. Basically, what we need to do is add to page table base register the virtual page number 2 times the size of a page table entry clearly, so that we can access the location in the appropriate page table entry in the page table. So this is page table entry 0 for virtual page number 0. This is page table entry 1 for virtual page number 1. And this is page table entry 2 for virtual page number 2. And you index and access the page table entry. In this case, page table entry says it's valid, meaning that it's in physical memory. And it gives the mapping. And the mapping says the physical page number associated with this virtual page number is 0x7FFF. So you take that, that's your physical page number, and concatenate to it the page offset, and that's your physical address now. So that's how you do the translation. Basically, we translated the virtual page number to a physical frame number. And in this case, the virtual page we're accessing happened to be in physical memory. That's what the val bit says. And now this is our physical address. Now we can access memory, physical memory with it. Make sense? So you need to do this for every single memory access. Whenever you're fetching an instruction, the address you have is virtual. the program counter is virtual. Whenever you're fetching the data for a load, the address that you generate is virtual. Whenever you want to store something to memory, the address you generate is virtual. For every single memory access, you basically generate a virtual address. Okay, so the page table provides the physical frame number or physical page number, as I said, and page offset bits do not change during translation because that's really the page size, and that indicates which byte in the page that you're going to access. Okay, so let's take a look at another example. This is, if somebody asks you the question, what is the physical address or virtual address 0x5F20, what do you need to do, basically? What does the processor need to do? First of all, it needs to find the page table entry containing the translation for the corresponding virtual page number, right? Just like what we did previously. So to be able to do this, you need to look up, and then it needs to look up the PTE page table entry at that address. So what is that address? That address is given by the page table base register, beginning address of the page table, plus the virtual page number times the size of a page table entry, clearly, right? Because if the size of, you basically want to find the address of the page table entry corresponding to this virtual page number. So that's how you calculate the address in memory to look up in the page table. So let's do it for this address. So what is the physical address of virtual address 0x5F20? Basically, you do this. You chop off the page offset, F20 in this case, the bottom 12 bits. It's easy to do. You know how to manipulate bits now. And the remaining top 19 bits are essentially the virtual page number now, and it happens to be 5 in this case, right? Now, you could have said that by just looking at this value. The bottom 12 bits are F20 over here, and the top 19 bits, remaining bits, are just 5. So our virtual page number is 5, which means that entry 5 in the page table indicates entry 5 in the page table is our page table entry. That's the page table entry we're looking for. And we index the page table with that entry 5. We take the page table base register, add 5 to it, times the page table entry size, of course. And it turns out, again, this particular virtual page happens to be valid, which means that it has a translation. It's already in physical memory. And the physical page number is 1, essentially. And now you know that the physical address is 1, and then concatenated with the page offset. So that's our physical address. Makes sense, right? So it's very simple. Okay. So let's take a look at another example. Now we're looking for 0x73E0. So we basically need to do the same thing. Locate the page table entry corresponding to this virtual page number for this address, and then see what happens. So in this case, the virtual page number is 7, because the bottom 12 bits are essentially the page offset. And we look at entry 7, which is the 7th entry from the bottom. And we do all of the calculations. So actually, the page table getting to this point requires memory accesses, as you can see. We're going to fix that problem later on. And it turns out, in this case, this particular virtual page doesn't have a valid mapping, which means that it's not in physical memory, right? So what do? Well, the remaining part in the page table hopefully specifies where is it actually. So one thing maybe it's not allocated. That's possible. So you need to actually scan that page table entry to figure out what's happening. If it's not allocated, what might this mean? The program generated this virtual address, and the page table entry says this is not allocated. Now you get an exception, right? Then the processor throws an exception saying that you're trying to access an unallocated virtual page. And then the operating system needs to handle that exception somehow. So these are actually really interesting questions that happen at the stack level. Okay, maybe in this case, let's assume that it's allocated, but it's on the disk. Well, in that case, you get a page fault. That's also an exception. And the exception says, okay, this virtual page that you're trying to access is allocated, but it's in the disk. So I need to bring in all of my system structures to actually take the page from the disk, put it into the physical memory in some physical page, and then tell you, okay, now you can proceed with the access. That's the idea of a page fault. Okay, so we're going to go through the page fault in a little bit. Any questions? Okay, this is all clear. But you guys haven't seen this before, right? No, okay. You'll see this more in systems programming. This is an area where architecture interfaces with the operating systems quite a bit. Okay, so there are a bunch of issues here. This is an issue I'm not going to answer, but keep this in the back of your minds. Actually, there are backup slides that talk about how to do this, and you'll cover this a lot more in the OS course. Okay, basically the page table is actually huge. There's an issue here. So assume that you have a 64-bit virtual address and a 4-kilobyte page. Your virtual page number is 52 bits. That's huge, right? Basically, you need to have 2 to the 52 entries in your page table. And assume that your physical address is 40 bits. Your physical memory size is 2 to the 40 bytes. That's what you do, basically. This is the translation. You need to convert a 52-bit virtual page number to a 28-bit physical frame number, and then calculate the physical address by concatenating the page offset with the physical frame number. So you've seen this before. So how large is the page table in this case? I think I've already given you the idea. You have 2 to the 52 entries times the size of the entry. Assume that the size of the entry is 4 bytes. That's 2 to the 54 bytes. That's a lot of memory, right? Where do you store this thing? Clearly, you're not going to store it in hardware on chip. Okay, let's assume that you store it in physical memory. Are you able to store all of this in physical memory? That's a lot of physical memory, right? 2 to the 54. Can someone tell me how big that is? 2 to the 30 is 1 gigabyte. 2 to the 40 is 1 terabyte, right? I don't know what 2 to the 50 is. Is it exabyte? Petabyte? Yeah. 16 petabytes, okay, that's good. It's petabytes, that's right. And then you go to exabytes after that. So it's 16 petabytes, that's a lot. So clearly you don't want this. So this issue needs to be solved. And this is actually just for one process. You actually need to have this for all processes that are running in the system, at least that are ready to execute, right? And and the process may not be using the entire virtual memory space. So actually, one question is, do you really need this huge page table? Because not all processes need that huge virtual address space, because they don't necessarily allocate data in all of that, right? Maybe some of them need very small. So there's a solution to this, which we're not going to cover. Basically, this is one of the challenges. At least part of it needs to be located in physical memory, because you need to be able to access this page table, right? You cannot say page table is also in virtual memory. At least not the complete page table can be in virtual memory, because you need to do the translation, and you need to get a physical address so that you can access physical memory. So at least part of this page table needs to be in physical memory. So what people have developed is the idea of multi-level or hierarchical page tables. You don't have a huge page table that looks like this. You basically have a small page table that you first index with a smaller number of bits over here, and that has to be in physical memory. There's no way of getting around that. That has to be in physical memory. And then you use that to index a next level of page table to do the address translation. And all of those other page tables don't need to be in physical memory. They can be in virtual memory, because you have a way of getting to them through the physical address translation, a virtual to physical address translation. Again, I'm not going to go through this. You'll see this more in the OS course. And if you're really curious, read the remaining parts of the chapter 8.4. And also I have slides related to this, which we can cover if we get to it, but we'll see. Does that make sense? Okay, cool. So a multi-level page table is a solution to the problem. But there's another problem. Okay, assume that you solved the capacity problem, and people solve this. There's another problem which may or may not be as serious. I think these are both serious problems. Whenever you're accessing memory, now you need 2 memory accesses, well, at least 2 memory accesses. Basically, whenever you're fetching an instruction, you have a program counter, it's a virtual address. You need to go to the page table to find the page table entry, which means that you need to access memory to do the translation first. And then after you do the translation, you have the physical address, you need to go to memory again to get the instruction. That's 2 accesses. That's true for load store also, basically. Basically, you need to do 1 access for address translation, page table read, and 1 access to access the data or the instruction with the physical address that you get after the translation. Because you added this indirection, you need to do the translation. You need to do a memory access for the translation. And this problem actually becomes worse if you have multi-level page tables, because if you have multi-level page tables, you need to do multiple memory accesses to get to the physical address that you need, which means that To be able to generate the physical address that you're really looking for, you're going to do multiple memory address accesses to just translate just for translation. Now that sucks, right? You just want to fetch an instruction, and you're doing 5 memory accesses to figure out the address of the instruction, and then you're actually going to access the instruction. So this is not good. And this, if you actually do this, just like we described, this greatly degrades the execution time, because basically for every instruction, you need to do at least 1 memory access to do the translation, and at least 1 memory access to get the instruction. So you basically double the number of memory accesses you do for every instruction, because you need to fetch every instruction, right? Unless you're clever, of course. And people are clever. People figured out ways to speed up this translation, and we're going to talk about that. So how do you speed up this translation? We're going to use an idea that we've seen before. Yes. Cache. Use a cache. Use a specialized cache to cache the translations, basically. Cache the page table entries. So you know the concepts now. You can apply it. That's why caches are very important. You have caches everywhere. So, okay, that's the idea of the translation Lookaside buffer. It's a very specialized cache, and its purpose is to just to cache the translations that you've seen in the past, or you've done in the past. Or, in other words, you cache the page table entries in a hardware structure in the processor to speed up the address translation. Let's take a look at what it looks like. So this is called translation Lookaside buffer. It's a small cache of most recently used translations. Like any cache, you can have different policies for it, of course. It reduces the number of memory accesses required for most loads and stores and instruction fetches to only 1. Because basically what you look up over here is you get the virtual address, and you look up this cache quickly, and if you hit in this cache, you can quickly translate the virtual address to physical address, because that cache already cached the virtual to physical address translation. So why does this work? Because page table accesses have a lot of temporal locality. If you're, for example, going through running a program and executing instructions, in the von Neumann model, it's all sequential, right? And if your page size is 4 kilobytes, and if each instruction is 4 bytes, there are 1,000 instructions in that 4 kilobyte page. You go to the first instruction, you get let's assume a page fault, you bring the page inside, and then you set up the translation. So you actually don't have the translation there. You pay all of the overhead, but when you go to the next instruction, the page table entry for that particular page that you're accessing is already in the TL.B, which means that you're going to hit in the TL.B when you access the next instruction, which means that you're not going to have to do another memory access, because this TL.B is actually very fast. It's on the processor, and it can be very small. Okay, so data access have temporal and spatial locality. So for the very reason caches work, translations for the addresses that you're actually trying to access also have a lot of temporal and spatial locality. And you may have a large page size, so that consecutive loads and stores and instructions are likely to access the same page. Actually, if you're streaming through instructions, it's good to have a very large page for instruction pages, and if your code is large, of course. That way you don't need to do the translation and populate the TL.B many times when you're actually executing sequential code. Okay, the true for arrays also, right? If you have a 1 gigabyte array that you're traversing through, you have a lot of spatial locality, and you don't, ideally you would like to do the translation only once, put the page table entry into the TL.B, and you never need to do the translation for those huge arrays. So that's why people have actually come up with large page sizes. Essentially in x86, for example, you have, I think you have gigabyte pages as well. So you can have very large pages. And if you know that your code is going to access very large pages, you might want to allocate those very large pages. Okay, so the idea of TL.B is it's small. You want to access it in one cycle so that you get the translation. And once you get the translation, you access the caches. Actually, there's a little bit more subtlety over here, which we may get into also. When do you do the cache access versus when you do the TL.B access? But assume that you do the cache access after you get the physical address. Then you basically do this access to the TL.B, get the physical address, and then you access the cache to get the data. Yes?
Can you have variable size for page size so that programs that use a lot of memory have a higher probability of cache hit?
So existing systems actually have multiple different page sizes. So x86 provides, I think, 3 different page sizes. Some of them are really small, some of them are very large, just for the reason you say. But they need to be used nicely. You need to know what you're doing, basically. Okay, so typically this is small. Actually, there are multi-level TLBs in existing systems. It's not just one level. You have an L1 TLB, and you may have an L2 TLB, because you actually have a large working set, and you want this L1 TLB to be really fast, and then, but you don't want to miss in a small TLB all the time, so there's a second level TLB also in many systems today. So you can see that we're adding more complexity into the system. We already have caches to cache the data. Now we're adding caches to cache the translations, just because we want to make programmers' life easier so that they don't need to worry about the physical memory management. Okay, usually TLBs are highly associative, so you don't want to have conflict misses, and typical hit rates are actually very large, but this depends on the workloads, especially workloads that do a lot of random access. They don't have a lot of good locality on these translation caches or TLBs. As a result, they get very poor hit rates in the TLBs. They get very poor hit rates on the caches as well. So they spend a lot of time doing the translation and then doing the memory access. So their performance actually degrades quite a bit. So clearly this depends on the workload, as you know. But when it works, when the TLB hits, you reduce the number of memory accesses for most instruction fetches and loads and stores to only 1, basically, because you access the TLB, that's a specialized cache, and then you access memory after that, or the memory hierarchy after that. Okay, so this is an example of a 2-entry TLB from your book. Basically, it's just like a cache, 2-entry, 2-way associative, or fully associative cache. And basically, what it caches is this. It caches the page table entry associated with a virtual page number in one entry, and the page table entry associated with another virtual page number in another entry. Make sense? And this is the val bit for the cache itself, not necessarily the page table entry. Because if you already have a translation for a virtual page number, that's assumed to be valid in this case, meaning in physical memory. So let's take a look at it. So in this case, the TLB has 2 entries, and both of them are valid. And one entry is for the translation for virtual page number that's specified by this, 7FFFD. And it happens that it maps to physical page number 0. And the second entry is for virtual page number 2, and it happens that it maps to 7FFF, which we looked at earlier. And assume that the processor is accessing this address, this virtual address, 247C. It does exactly the same thing. Basically, you need to figure out what's the virtual page number, and you use the virtual page number to index into the TLB. And TLB has 2 entries, which mean 2 entries, and it's fully associative, which means that you compare the tags in the TLB, the virtual page number, to the virtual page number that you're searching, right? And this is very similar to a fully associative cache lookup, right? You basically bring the tags or the virtual page numbers that you've stored, compare them to the virtual page number you're looking for, and you'll get a hit signal if you have a match in any of the entries. And in this case, there's a match in entry 0, as you can see. And what do? You take the physical page number from entry 0, so you get a hit for entry 0, and take the physical page number, concatenate it with the page offset that you have from the virtual address. And that's how you do the translation. It's, in some sense, similar to a page table, but it's not a page table, it's a cache of the page table entries. Make sense? Now, the next time, if you keep accessing a virtual page 2 all the time, you always hit in the TLB. So this translation is very, very quick. You don't need to access the page table in memory because you've cached the right entry. But if you miss in the TLB, meaning, for example, if you're accessing virtual address 10, virtual page number 10, clearly it's not in the TLB, in this 2-entry toy TLB, which means that the TLB will say you missed in the TLB, so you don't have the translation. Now you need to go through the page table just like we discussed. And that requires a memory access to the page table. That takes a lot of time. Page table gives you the translation, you have the physical address, you store the translation into an entry in the TLB by kicking out another entry, because it's a cache of translations, cache of page table entries. And the next time you access virtual page 10, you hit in the TLB, because the TLB stores the recent translations that you've done. Make sense? So it's a simple concept, but it improves performance, just like caches. But now you can see the complications we're adding to the system. Okay, so let's go a little bit more into detail. So support virtual memory, we've added now multi-level page tables, which we didn't describe in detail. You'll see more. We've added TLBs, translation look-aside buffers, and actually now you don't have a memory hierarchy only. You also have a translation hierarchy on the side. You basically have levels of TLBs, and also there are also actually in existing systems specialized structures. x86, for example, has specialized hardware to do this page table walk, page table access, and page fault handling. So there's hardware dedicated to do this page fault handling inside the system. So there's a lot more to do to support virtual memory. Basically, it requires both hardware and software support. So page tables in memory, as we discussed, it can be cached in specialized hardware structures called the translation look-aside buffers. And the hardware components in general that helps you access memory is called the memory management unit, MMU. So if you hear about this, if you've heard about, how many of you heard about MMU before? Okay, some of you did. So this is what is, what really, it's really the translation and access control structure for the memory management unit. And it includes many things. And this is not a comprehensive list. It includes a page table base register for every process that's running. It includes the TLBs, so MMU is actually a bigger distributed structure on chip, so TLBs are very close to the processor, but MMU includes them also. It also includes the machinery or hardware to access the page table whenever you actually have a TLB miss. And it includes the machinery to do to bring in the page from disk into main memory if you actually have a page fault. So TLB miss is different from a page fault, right? TLB miss means that the translation page table entry doesn't exist in the translation look-aside buffer, so you need to go and access the page table. Now you go and access the page table may tell you the page actually, the virtual page is actually allocated, is in the physical memory. That means that that's good, no problem. But if the page table tells you the page is not in physical memory, that's a page fault. So a page fault indicates whether the page that you're trying to access is in physical memory or not. And the TLB indicates whether the translation that you're trying to do, the page table entry that you're looking for to do the translation, is in the TLB or not. So these are two different things. You can get actually, you can get different situations, which we're not going to go into right now. Okay, so it's the job of the software to actually leverage the memory management unit to do many things. Populate the page tables, decide what to replace or what to place in physical memory. We're going to see examples of this also. Change the page table register on a context switch. Whenever you actually assume that you have a single context in your machine, single thread, you have a single page table base register that points to the page table, beginning of the page table of that process. Now, when you change the process, when you start running another application, that application has another page table base register, so that needs to be changed. So there's machinery in the system to actually change that also, because you cannot use some other thread's page table clearly, right? And the software also leverages the memory management unit to handle page faults and ensure correct mapping between the physical memory, correct mapping inside the page table between virtual memory and physical memory. And we will see examples of this quickly. Okay, address translation we talked a lot about. I'm going to go through it quickly. Basically, how do you obtain the physical address from a virtual address and page size specified by the ISA? In the past, the page sizes were small. WAX, for example, that's digital equipment's old architecture, had 512 byte page sizes, which were small. Today, we're actually growing bigger. 4 kilobytes is common, 8 kilobytes is also common. These are small pages by today's standards. And we also have very large pages as well, 2 gigabytes for the reason that I discussed. If you're streaming through memory, you don't want to keep getting translation misses or page faults. And today you can use different page sizes with some effort. And there are trade-offs associated with it. Remember the cache lectures. Similar trade-offs exist also here, right? If you have a small page size, and if you have good locality, then it's better to have a larger page size in this case, right? Again, I'm not going to go through the trade-offs of this one here. It's very similar to the block size trade-offs that we had in caches. Okay, so page table entry contains an entry for each virtual page. Let's go into that a little bit more. It's called a page table entry. We've already discussed this. This is just for your benefit. What's in a page table entry is interesting because there are more things than we've discussed so far. So you can think of page table as a tag store for the physical memory data store. That's another way of thinking about it because really physical memory is a data store and page table tells you what data really exists in this data store compared to all of the things that you can have in virtual memory. So it's a mapping table between virtual memory and physical memory. And page table entry is a tag store entry for a virtual page in memory. So you need a valid bit for that reason. Basically, this indicates the validity or presence of the virtual page in physical memory. And we've already discussed that. You've already seen an example. You need tag bits or physical frame number or physical page number to support the translation. If a mapping exists for this virtual page, you need to get the physical page number. So we've seen that. You need bits to support replacement. So, okay, let's assume that your physical memory is full, meaning that all of the physical pages are allocated and they're already filled with data from the disk. Now the process tries to access another virtual page, which is not inside the physical memory. So what needs to happen? You need to kick out something from the physical memory, right? So what do you kick out? That's one question. In caches, you have the same problem. Your cache is full, or set is full, and you need to kick out a block because you're going to bring in some other block. So you need to have replacement policy bits for that reason. We're going to see an example. In this case, though, the replacement is a bit harder because you have a huge number of pages, right, in the system. Okay, you need to have a dirty bit to support write-back caching, meaning whether you've actually written to this page, should you write it back to the disk or not. You need to have protection bits to enable access control and protection. We're going to talk about this. This is actually a separate function of virtual memory. Virtual memory has two orthogonal functions. Address translation is something that we've been focusing on. We're going to focus on it a little bit more. And then I'm going to switch to memory protection. That's also very important. And we discussed this yesterday. It provides isolation between different processes. It also provides access control to different pages. So you may not be able to give complete access to every single page for a given program, right? So you want to check access permissions. So we're going to talk about that. So to be able to do this, you need to have protection bits on a per page basis. And this is my cartoonish picture that shows a page table entry. Basically, valid bit, dirty bit, some replacement policy bits. In this case, I have a single bit over here. This basically says it's a reference or access bit. If a page has been recently referenced, you set this bit. If a page has not been recently referenced, you clear this bit. And operating systems actually use this bit to do the page replacement on a page fault. And there are protection or access control bits. Can this process access the page? What level of access does it have? We'll talk about that a little bit. There could be other bits, as you will see in the backup slides. Backup slides have an example from x86 architecture. And of course, you need to do the translation, assuming that this is valid. Physical frame, the page is stored in, if the page table entry is valid. So address translation, and you've seen this before, this is a more generalized form. Again, I'm not going to go through this. Basically, you take the physical frame number from the page table entry. Okay, I think that's another picture. And I already said a lot of this over here. This is for your information. Maybe this is an uglier picture, but... Okay, so let's take a look at what happens after address translation. There are two outcomes, right? You get a page hit, and this is another view of the system. Processor generates a virtual address. It interacts with this memory management unit. Memory management unit is the address translation and protection unit. Basically, it's the virtual to physical memory access unit. It does include the TLBs, page walkers, page table base register, everything. So processor sends virtual address to the memory management unit. That's the first thing. And MMU fetches the page table entry from the page table in memory and caches it potentially and does the translation, right? So basically, MMU initiates a page table entry access from memory, and it gets the page table entry. Oh, sorry. And after that, it does the translation, which means that it gets the physical address. Now it sends the physical address to the memory hierarchy, and it gets the data and gives it back to the processor. This is a clean separation of translation accesses and the data accesses that you need to do. So this translation unit mediates your access to memory, essentially. It also tells you you cannot access this page, for example. Or if this page is not allocated, you get a fault saying that you're trying to access a page that you're not allocated. Okay, so hopefully this is clear. So this MMU includes the TLBs also. It doesn't always need to do this access if the data hits in the if the virtual address, virtual page number hits in the TLB over here. Then it quickly gets the physical address and accesses cache and memory with that physical address and brings back the data. Okay? So this is the good case, of course. You get a page hit. If you get a page fault, which means that the virtual page you're trying to access is not in physical memory, then you need to do more. So let's take a look at that case. So processor sends the virtual address to the MMU, just like usual. And MMU fetches the page table entry from the page table in memory. So it gets the page table entry. And it figures out the valid bit is 0, meaning that the physical memory actually doesn't have this virtual page. So MMU triggers some page fault. So this is an exception. We talked about precise exceptions, right? This is where precise exceptions matter, actually. This is when you start the exception handler and you transfer control to the operating system from the process. You basically finish the process at the point you got the exception. All instructions before the instruction that is causing the exception are retired. No instruction after the instruction that is causing the exception actually did anything. So you have a precise state. And then you tell the operating system, I got an exception, a page fault exception in this particular instruction. It could be because of you're trying to fetch the instruction or because you're trying to fetch the data for the load store instruction. And now the operating system kicks in, starts the exception handler, and it basically needs to figure out what to do. So what to do means, first of all, the operating system figures out that there's a page fault exception, and it gets the address, it gets the virtual page number, it gets and it's basically, the first step is looking at the page table entry and identifying what to bring in to the physical memory. And it also needs to identify the victim. What does that mean? Basically, physical memory is full. That's why you got a page fault. So the operating, or maybe physical memory is not full. You need to find a place in physical memory to house this virtual page in, right? Assuming the physical memory is full, all physical pages are valid. Well, the operating system needs to figure that out also. See, I'm not telling you exactly how the operating system is doing that. There needs to be data structures in the operating system to figure that out. And that is also expensive, actually. This is actually, many operating systems use inverted page tables to be able to do that. They have a mapping from the physical page number to virtual page number also internally, and that becomes a mess, but you need to do it. Basically, you need to figure out the victims, and if the victim page is dirty, you need to write that page to the disk. Let's finish the page fault handling, and then we'll take a break. You need to write that page to the disk, first of all, and also bring the new page that you're trying to access from the disk into the physical memory. So handler pages in, this is called paging in the new page. And you need to update the page table entry clearly, because now you're bringing in a new page into the physical page number, and you update the page table entry to be valid, and you store the page, physical page number. And after that, after all of this is done, the operating system returns control to the original process, restarting from the faulting instruction, which means that it needs to bring in the process back into the processor, and hopefully at that point, that instruction executes again, and now it does the translation again, and hopefully everything is in the TLB at this point, because the MMU ensure that the translation gets into the TLB, and then it accesses memory, and then it may get a cache miss for that page, for that location it's trying to access, right? Because this page was not in physical memory, so it should not be in the caches also. So after the translation, you'll get a cache miss to be able to access the first data that you're trying to access for that particular page that you brought in. So now you can see a page fault is actually pretty costly, right? Because you not only get a page fault, do all this translation, bringing the data into the physical memory. On top of that, you'll get a cache miss as well. Okay, so let me finish the page fault. So if a page is not in physical memory but disk, page table entry indicates virtual page is not in memory. As I said, access to such a page triggers a page fault exception. And as I said, OS trap handler is invoked to move data from disk into memory. The good news is other processes can continue executing. While this is happening in the background, other processes can be executing if you have other processes. If you don't have other processes, tough luck, you'll need to wait for this page fault. And OS has full control over this placement, and we're going to talk about that. So basically, this is what happened. Before fault, you're trying to access this particular page. That page is not in physical memory, clearly. It's in disk. So you call the OS, please help me. And after fault, what it looks like is the OS has allocated the page, placed it into a physical page number, and now you have the mapping. Now after the fault, you can do this translation fine. So you don't need to go to the physical memory. Okay. So let's go through this. Basically, how do you service a page fault? Essentially, the processor needs to signal some controller. In this case, it's the I/O controller, because you're really trying to access the disk. And tell the I/O controller, read block of some length, starting at disk address X, and store starting at memory address Y. And these addresses are known by the operating system, basically. The operating length P is essentially the page size. You may need to do multiple of these, because the access granularity to the disk may be smaller than your page size if you're bringing a 1 gigabyte page. Usually the access granularity to the disk is actually maybe 512 bytes or 1 kilobyte. If you have a 4 kilobyte page, you need to do this, access the disk multiple times. The good thing is hopefully you're accessing the disk in a streaming manner. And then you know the address X from the page table, and you know which physical memory address you're going to put the data into, because you just figured out where you're going to place this page into. So the operating system actually handles this through the processor. That's the initiate block read part. And a read occurs from the disk, SSD, whatever you have. So the I/O controller handles that. And actually, in today's systems, there's a direct memory access engine, which ensures that the data doesn't go through the processor, but the data gets transferred directly from the disk into the memory. This is called direct memory access. So you set up a controller over here in the memory controller, which essentially orchestrates this movement of data from address X in disk to address Y in physical memory. And then once the DMA controller is done, it says, I'm done, it interrupts the processor, and the remaining part of the page fault handler finishes, and the OS says, okay, the data is ready, now processor, you can execute. Okay. So that gives you the full system picture. But of course, there is a lot of detail related to DMA, which we're not going to go into. And clearly in this course, we haven't even touched the storage. But that's a huge system also out here. Okay, this is probably a good place to take a break. After that, we're going to talk about page replacement algorithms very quickly. Okay, let's continue. Some of you asked very good questions, like who initializes the page tables? How does the system start up from the beginning? These are all very good questions, but they're really things that we have not covered, and we really don't have time to cover. You can think about these on your own, but you won't be responsible for any of those. I'm just giving you a broad overview of the virtual memory system. You may or may not get answers to those questions in the systems programming or operating systems course. I don't know, I'm not sure. But this is essentially somebody needs to initialize the page table to begin with, right? Usually what happens is some firmware plus the operating system together initialize the process page table such that the page table points to locations in the disk where you need to load the pages from into the physical memory. So page table also has pointers to the disk if the entry is not valid, if you remember. So somebody needs to populate those. But we cannot cover all of that. There's a lot of complexity in the system, and this is a part of the system that actually touches a lot of things. You can see that we're touching the disk, we're touching the memory, we're touching the caches, we're touching the translation structures, we're touching both hardware and software. So we cannot possibly cover all of that, but you can think about how to do it. And it's a complex part of the system. It's not a simple part. Okay, let's talk about page replacement. So I've already discussed the problem. If the physical memory is full, which means that the list of free physical pages is empty, so I'm introducing something here. Somebody needs to keep a list of free physical pages, and that's the operating system. Because the operating system, whenever it gets, it needs to allocate a physical page to a virtual page that is in the disk, it needs to say, okay, I have these free physical pages, so let me allocate one. So the operating system has these data structures to enable virtual memory, and that's one example data structure. So if that list is empty, meaning physical memory is full, which physical frame do you replace on a page fault? So essentially, this is very similar to cache replacement. And if you think about the virtual to physical page mapping, it's really a fully associative mapping. The operating system has complete freedom to, in terms of which physical page in the physical memory it can map a virtual page to. So a virtual page, any virtual page can be mapped to any physical page in physical memory. So it's really a fully associative mapping that you can do, which means that you actually have a lot of freedom in terms of what to replace also. You can basically pick any page in physical memory that's already there, and you can say, I'm going to replace you because you have not been used for a long time, right? That could be one way. Or you have not been used very frequently. But of course, we've seen some replacement algorithms for caches. One of them was true LRU, meaning true least recently used algorithm. So if you want to figure out, assuming that you want to figure out which page is the least recently used one, and if you want to figure that out, you actually need to do a lot of, store a lot of metadata. So basically, if you have 4 GB of memory and 4 KB pages, now you can count how many pages you have, right? 4 GB is 2 to the 32, 4 KB is 2 to the 12. That's 2 to the 20 pages. Essentially 1 million pages. Now, what does this mean? If you really want to figure out which page is the true least recently used page, you need to maintain an ordering of all recency of use of each page. Now, that ordering is actually very complex. And we didn't do this exercise, but if you actually want to figure out how many possibilities are there of that ordering, that's 1 million factorial. Basically, there are 1 million different factorial ways you can order these pages, and all of them are possible. And you need to update those orderings if you really want to figure out which page is the true least recently used one. Because whenever you access a page, you change the recency of use of that page, right? So this is, it can get very complicated, so you cannot implement least recently used algorithms in such a cache, if you will, because the cache has just too many entries in it, 1 million entries in this case, right? Okay, so modern systems use approximations of LRU. I'm going to give you the key idea of an algorithm that many operating systems build on. They don't use the exact same algorithm, they actually build on that algorithm. And that's called the clock algorithm. It was developed a long time ago. And more sophisticated algorithms actually take into account not only recency of use, recency of access, but also frequency of access. How frequently are you accessing this particular page? And if you're accessing that frequently, you should not replace it. And if you're accessing, and usually they combine a metric of frequency and recency together. If you're accessing things frequently and also you've accessed them recently, keep them in physical memory, don't replace them. And other stuff that you haven't accessed frequently or recently, kick them out. And our ARC algorithm is one example. It's actually a very interesting algorithm that was published like 16 years ago, and it's employed in some of the Linux systems. And you can take a look at that. And you can see the title, right? ARC, a self-tuning, low-overhead replacement cache. They're treating physical memory as a cache, as you can see. So a more basic algorithm that people have developed and many operating systems use is called the clock page replacement algorithm. It looks like this, basically. It looks like a clock. You order the pages, and in this case, assume that you have 1 million pages based on the thing that we've done. And you have a pointer that basically, you can think of this as a clock. And that pointer points to the place that you're going to start looking for a page to replace. So it points to this page, for example. And it basically tries to find a page whose reference bit is not set. So I assume that these are bits for each page, saying that this page was accessed recently. So it starts from the clock handle, it starts turning this way, it visits every single page table entry, and basically says, has this page been accessed? If it has not been accessed, it's going to be replaced. If it has been accessed, then you're going to clear the bit and go to the next page, until you find a page that has not been accessed. So that's the idea. It's a very simple idea. You just have one single bit per page, or per page table entry, and the clock starts at one position. It looks for the first page that is not accessed recently, that doesn't have this bit set. And while it's going, it clears the bits of those pages whose access bits are set. So the next time you visit them, they're going to be 0, or they're going to be 1 if somebody actually accessed them between the time you visited them at this point and the time that you visit them next. It's a simple idea, as you can see, right? So how does it work? Basically, you keep a circular list of physical frames, physical page numbers in memory. The operating system does. This is where an inverted page table comes in handy, but we're not going to go into that because this is really a physical frame, so you really want to look at the physical frames. And you keep a pointer or hand to the last examined frame in the list. And when a page is accessed, you set the reference bit in the PTE. These are the reference bits over here. And when a frame needs to be replaced, you want to figure out which one to replace among all of these. You replace the first frame that has the reference bit not set. So in this case, you replace this one, and then go to the next one. And you traverse the circular list starting from the pointer. You go clockwise. That's why it's called clock. You can think of this visually that way. And during traversal, as I said, you clear the reference bit or access bits of the examined frames so that the next time you come to them, you can replace them, assuming they're not going to be accessed in between, right? And then you set the hand pointer to the next frame in the list after you do the replacement, so that the next time, the thing that you're going to consider for replacement is not the page frame that you just replaced, that you just allocated. You just move to the next one. So this has a lot of interesting properties. It's very simple, first of all. You can cover all of the physical memory space, and you're not going to replace the thing that you just put in physical memory the next time you come back, because you're starting from the next one in the circular list. It's actually the last thing that you're going to examine for replacement the next time you try to do a replacement, meaning that the next time you get a page fault, right? Okay, so that's the idea. And that's the basic idea. A lot of algorithms are based on this. How does it perform? You can take the systems programming course. Okay, so this is one replacement algorithm, actually. Basically, we're trying to replace a page from the physical memory. And it's essentially similar to cache replacement. You could use the same algorithm for a cache, for a set-associative cache. Actually, it works not so unreasonably for a large set-associative cache. But it shows that physical memory is a cache for disk. It's managed by the system software via the virtual memory subsystem. And page replacement is actually similar to cache replacement, but there are differences which we will talk about very briefly. So page table is really the tag store or physical memory data store, as I said. So what is the difference? So the difference is actually, one difference is based on the access time. So whenever you're doing a replacement, in a cache, you want to be relatively quick, because cache access latencies are very small. But now we're dealing with physical memory. Physical memory access latencies are very long. So you can actually have more sophisticated algorithms. And in fact, clock is a little bit sophisticated, but people have developed more sophisticated algorithms. So the speed of access is one difference. A cache, you need to access in a few cycles. Physical memory, hundreds, 500 cycles. The number of blocks in a processor cache is very small compared to the number of blocks in physical memory. In the example that I showed you, even with a 2 GB memory, I think it was 4 GB. 4 GB memory, you get 1 million cache blocks, 1 million pages. You don't normally have 1 million pages in a processor cache. It's actually much smaller. So that actually impacts the replacement also. This makes actually replacement a bit harder in physical memory. This makes replacement a bit easier in physical memory because you have a lot of time to figure out the victim. Here, even though you have a lot of time to figure out the victim, you have a lot of potential victims to replace. So it goes, they oppose each other a little bit. So I already said this, basically the tolerable amount of time to find a replacement candidate, disk versus memory access latency, that is very different. So in disk latency, you can actually take time to figure out which one to replace. And the role of hardware versus software is probably one of the most important. Normally, the caches that we have on processors is not managed by software. They're managed by hardware, as we've discussed. But in this case, we're managing the cache, physical memory, via software, right? The clock replacement algorithm is done by the operating system. Because you need huge data structures. You can manage this in hardware also, but you get into a lot of hardware overhead if you actually want to do the replacement in the hardware. So the management of the physical memory is usually done in software. Any questions? Okay, so let's talk a little bit about memory protection, which is another part of the virtual memory system. I've already said some of these things. So basically, multiple programs, processes run at once, and each process has its own page table. Each process can use the entire virtual address space without worrying about where other programs are. And this is beautiful, because if you were to deal with physical addresses, you don't have this luxury. Now you have to worry about where other programs are, and it's a huge mess. But virtual memory, by enabling this indirection and having a virtual to physical mapping for each process, saves you from a lot of headache, because you don't need to think about other programs. So a process can only access physical pages mapped in its page table. It cannot overwrite memory of another process. So that's beautiful, right? It's memory protection, basically. So it provides protection and isolation between different processes so that they don't touch each other's data. They cannot read each other's data, they cannot write to each other's data unless they specifically share a page. What does sharing a page mean? Two different virtual pages in different processes are mapped to the same physical page. That's how sharing is done through the virtual memory. And if you want to do that in an operating system, you go through a special system called like SHMEM library, shared memory library in Linux. And that's how you allocate these shared pages. But otherwise, if you don't do that, you're completely isolated between different processes. And on top of that isolation, you have levels of access protection. So you can have access control mechanisms per page. Because for each page, you can specify what this particular process can do to the page. Can it read it? Can it write it? Can it execute it? This is how you can actually communicate between different processes also. For example, they're part of the operating system pages that can be mapped to the virtual memory of a process, so that the process can write something to that page and the operating system can read it, or vice versa. But you may not be able to, you may not want to give permissions to that process to execute code on some of those pages potentially, because the operating system should probably be able to execute that code in those pages, right? So that's one example. So basically, you need access control mechanisms to enable, to ensure that each process doesn't go beyond its protection boundaries. And we'll see some examples of this very quickly again. Okay, so basically, page tables per process. Each process has its own virtual address space. So this is one process one. It has a page table. This is another process 2. It has a page table, and they go through address translation mechanisms. So each process sees the full address space, virtual address space, of course. And you can see that this simplifies memory allocation, sharing, linking, and loading. The operating system handles a lot of these. So if you look over here, in this case, virtual page 2 in the virtual address space for process 1 maps to physical page 7. And virtual page 1 in virtual address space of process 2 maps also to physical page 7. Why? Because it looks like it's a read-only library code. So for example, this could be a library that gets mapped into physical memory, and they both actually reference that library. It could be shared data, it could be code, it could be different things, basically. Okay? So you can now share data as with this mechanism. You can also isolate pages, as you can see. This page cannot be accessed by this particular process because there's no mapping. And also, yeah, exactly. And also, you can specify access control protections. So let's take a look at that, basically. Access protection, access control via virtual memory. I'm going to give you, again, a high-level overview. There's a lot of detail that is here. So virtual memory enables page-level access protection, basically. Not every process is allowed to access every page, clearly. For example, you may need supervisor-level privilege to access system pages. But to be able to communicate between the system and processes, you may actually want to have read privilege to some of those pages. So the basic idea is very simple. You store access control information on a page basis in the process page table, and enforce access control at the same time as translation. So these are completely different things, actually. Address translation is there so that you have the illusion of infinite memory, and also you have other benefits related to address translation, as we've discussed. Access control is there for security, for isolation, for protection, right? But we actually combine them in the page table structure, because page table structure happens to be a nice substrate to store both types of information. So a virtual memory system, as a result, serves two functions. One is address translation, and the other is access control. So let's take a look at the address translation. I think I also have a nice handwritten picture over here, if it's not clear. Okay, so this is one example, basically. We extend the page. Essentially, if you want to use virtual memory for memory access protection, which essentially every system today does, if they have virtual memory, you need to extend the page table entry with the permission bits or access control bits. And whenever you want to access a particular page, essentially, the MMU, Memory Management Unit, checks whether the access privileges are enough to access that page. Can you do a store to the page? Can you do a write to the page? Can you read the page? Can you execute the page, for example? Different levels of permissions are there. And if you don't have the permission level to do the operation that you're trying to do, then you get an access protection exception. And that exception is thrown by the hardware, MMU, that checks it, and that needs to be handled somehow. It could be that your process terminates immediately, right? Because you're trying to do something that you're not supposed to do, right? So that's the idea over here. Again, for example, this picture shows that virtual page 0 is readable by this process, but not writable. And it happens to be here. And it's shared with process J, which has different permissions to that page, as you can see. It can read and write to it. So you can enable this process, which may have higher privilege for that particular page because it owns it for some reason. It may be the system that's trying to write something to communicate with this other process that's a user-level process. User-level process cannot write to it, but it can read from it, so it can get information from the system. So there could be many, many reasons, of course. Now you can build a lot of structures on top of this while keeping data private or protected, right? Okay, so these are the privilege levels in x86, right? And operating system has the highest privilege. And then after that, there are different service levels by the operating system. And then applications actually have the lowest privilege. These are called rings in x86, yes?
Does that imply that within one physical page, all of the data has the same protection?
Exactly.
So it's impossible that the data has to be structured in a way that they don't overlap.
Absolutely, yes, absolutely. So the granularity of protection is now on a page basis. And people actually have, that is not necessarily a good thing. If you want to protect smaller data elements, now you need to allocate them on their own page, basically. And people try to actually have fine-grained protection, like you want to protect bytes, for example, sometimes, because that byte is very important. You want to protect keys, for example, that are much smaller than pages, but you cannot do that in page table-based protection systems, like we've discussed. That's a very good point. And that's a research topic, actually. How do you get fine-grained protection mechanisms such that you can protect different granularities of data? One of the big problems with virtual memory today is your granularity is very fixed and rigid. You cannot change the granularity easily, and as a result, you cannot get different granularity address translation and different granularity protection. Okay, so again, I'm not going to go through this, but if you look at the x86 manual, it tells you how basically what kind of access control you can have for a page given the permission levels that are specified by the page table entry. You don't need to worry about this, but this is an example. So you can have user level privilege, you can have read-only access type, and supervisor level privilege, read-write access type, different access types as you can see. Okay, so I'm going to go back to lecture 1 right now, lecture 2. So we're assuming a lot of things over here, right? Memory protection is actually really great, but now we're going to go down the stack, and I'm going to ask you the question, what if your hardware is unreliable and someone can flip the access protection bits? And you know how to do that, I think, such that a user-level program can gain supervisor-level access and can access to all data in the system by flipping the access control bit from user to supervisor. Do you know how to do that? Yes? Exactly. So that's one way. So I'll go through this again so that we can tie lecture 1 and 2 to lecture 25. And hopefully you'll see the connection between these different levels. So we've actually built up all the way for protection mechanisms, but actually you really need something reliable at the bottom. So that's row hammer, essentially. I'm going to go through this relatively quickly. Essentially, you can predictably induce errors in most DRAM memory chips. But this is not the only mechanism, actually, it turns out. This is the most practical mechanism to do the attacks. But if you actually want to change the protection bits, you need to induce errors in memory. You need to make your hardware unreliable. But one way in the past, before we discovered row hammer, in the past, what people had done is written papers where they actually took a light source, a heater essentially, and physically took it to the memory, and that caused a lot of bit flips because you're heating memory up. And they actually used that to take over a system. Of course, it's a probabilistic attack, but essentially what it does is it flips some protection bits in your page tables or in your protection structures such that you can gain access to the system. Of course, this is not a great way because you have to have physical access to the memory to be able to do this, right? The interesting thing about row hammer is you can actually do this in a programmatic way. You don't need to have physical access to it. You actually don't need to be running programs on this particular system. You can actually remotely induce these row hammer flips, as I will briefly describe over here. Yes?
Does that imply that if your computer or your system runs harder than another system, it's less secure?
So it could be. That's a great question, basically. There's certainly a relationship between heat and reliability. And if you're running things at very high temperatures, you may actually be getting more errors. So temperature has a correlation with the reliability. And if you're actually running things at a much higher temperature than the thing is designed for, you definitely have a security problem. So that's another way of potentially doing an attack, right? Okay, so let me go through this because I think this is really important, and hopefully this will tie in a lot of things in this course. So we discussed row hammer, right? So does everybody know what row hammer is? Yes? So some people don't know, so I'm going to go through this quickly. It's essentially a simple hardware failure mechanism that can create a widespread system security vulnerability. And actually, I would recommend you reading this POP article. It's a nice article. So basically, the idea is cells are too close to each other, and there's electromagnetic coupling between the cells. So if you keep activating a DRAM row, like this, activate, precharge, activate, precharge, activate, precharge, activate, precharge, it turns out some cells in the rows that are physically adjacent flip from 1 to 0 or 0 to 1. If you really want to know exactly how they flip, you can read the papers related to it. Yes? So that's one way of fixing the problem. I'm not going to talk about the solutions, but increasing the refresh rate is actually not so good. Say it again?
Crippling the battery life.
Exactly, crippling the battery life, crippling your performance. So that's not a good solution, yes. So this is a hammered row, these are the victim rows. So basically you can flip bits. Even though you don't have any access to this victim row, you may have access to this row. You just need to have read access, not even write access, because whenever you have a read access, you're actually activating the row. And you do it many times before the cells get refreshed. And it turns out in most DRAM chips that you can buy today in physical memory, you can flip those victim rows, the vulnerable bits. So when we actually wrote the paper, this was the program that my student wrote, a 6. Now you can now empathize with this program a lot more compared to lecture 2, right? This program has 6 instructions. It basically what it tries to do is it tries to activate rows X and Y in an interleaved manner. So now you actually know pretty much everything in this hierarchy. To be able to do this, you need to go into the physical memory and activate it, which means that you need to bypass the caches, right? So you need to flush X and Y from the caches. And then you need to avoid row hits in DRAM. So you need to actually do this, do the activate access to X and Y in an interleaved manner. And that's what the program does essentially. You have the CL flush, cache line flushes, and you need defense. You may not need defense actually, but that's okay. You don't need to worry about that. You don't need to worry about what that is for now. You can read the paper. But basically, this is what this program does. And you can download it, run it on your computer if you want. See if you get errors. I'd recommend that. It doesn't always work because, yeah, it depends on what kind of system you have, because several of our proposed solutions are in existing systems to protect against this right now. Anyway, so if this works, then you have a problem, right? So basically, I think you've seen this before, but I'm going to give you the context better right now. Now you know about memory protection and all of these software infrastructure that people have built to protect one page from another page. That's essentially memory isolation or memory protection, right? And that's a key, this is the first sentence from the paper that we wrote in 2014. It's a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. We're violating this key property with this. So any protection mechanism that you build, assuming this property is useless. That's essentially what, that's the importance of the reliability of hardware at the bottom. So, and when we wrote the paper, we said that actually you could design an attack that hijacks the system, takes over the system. And essentially, these folks from Google Project Zero, these good folks, Thomas Dullian and Mark Seaborn, they basically showed that. And now that you have a lot of background, I'd recommend reading this particular blog post if you're interested. They did beautiful security engineering. And this actually, the slide is an exact copy, paste from sentences from that particular blog post that they published, saying that they actually exploited the DRAM row hammer bug. They called it a bug. I call it a failure mechanism, because this is really a failure, fundamental failure mechanism that is there, and they, to gain kernel privileges. And this is copy-paste from their work. They said they learned about the problem from our paper, and they tested a selection of laptops and found that a subset of them exhibited the problem. And they actually built 2 working privilege escalation exploits. That's essentially, what does this mean? They're escalating privilege. They're doing, they're able to do something that the process is not allowed to do. It doesn't have permissions to do, right? And you can read the paper for the other one. The other one's interesting, but not as interesting. It basically takes over the Google native client. You can think of this as taking over a virtual machine. But the other one is, the one that's written here is very, very interesting. But again, I'm not going to go into the detail a lot. There's a lot of beautiful security engineering that you need to do. You need to understand how bits flip. You need to basically understand where page tables are. And basically, if you understand all of that, you can construct an attacker program at the user level with 0 privileges, except privileges of accessing particular memory. And that program can induce bit flips, and it can gain kernel privileges on x86 64 Linux. What does that mean? Basically, it can access all the data. And that is what they say, unprivileged user land process. What it does is essentially, it's able to induce these bit flips in the page table entries. So when run on a machine vulnerable to the row hammer problem, the process was able to induce bit flips in page table entries. Now, what does this mean? We've seen the page table entries right now. Right now, this blog post will make complete sense to you if you actually read it. Of course, there's a lot of detail in security engineering. So what they were able to do was actually, they were able to induce a bit flip in the page table entry of a process, and they were able to flip the read-write bits, and they were able to gain access to all of physical memory. Make sense? And you can do this with what they've done. There's more detail, which I'm not going to go into, but it's actually very beautiful. So it's a bit sad, because you built all of these protection mechanisms to protect, but if the hardware is not reliable, then there's a big problem, right? And in this particular case, it's not just that hardware is not reliable, it's predictably unreliable. meaning that if you're able to induce a bit flip in a particular memory location, you can do it again and again and again and again for the same bit, for the same memory location, which means that an attacker has all the time in the world to figure out which memory locations are vulnerable. And it can wait, basically. It can figure out, maybe in stealth mode, figure out which bits are vulnerable. It can build a profile of your machine. And when the right time comes, it launches the attack. And other people have done this, actually. And as a result, people actually draw pictures like this. I'm going to give you an example of the attacks. If you're interested, you can do the readings. I'm not going to go into detail. But one of the hackers on the internet actually summarizes the Rollhammer attack like this. It's like breaking into an apartment by repeatedly slamming your neighbor's door until the vibrations open the door that you're after. That's actually a very good description, I think. It's good to see these insightful descriptions. Okay, so these folks basically showed that you could induce these attacks on systems of website visitors by doing this Rollhammer attack on JavaScript. Again, I'm not going to go into detail. You can read if you're interested. But I'll talk about this one because it's very interesting. This work showed that you could do this attack on an Android phone. And actually, they used to have an app on Android. If you have an Android phone, you can download their app and make yourself vulnerable to their attack if you want. What they did in this work is they've shown that they could profile a cell phone's memory and figure out which parts of memory is vulnerable, which bits they can flip. And what they did was, because they knew exactly how the operating system worked, how it allocated the page tables in the physical memory space, and how it really allocated pages, they were able to fool the operating system in a deterministic way to allocate a page table entry, a vulnerable page table entry, to a location that they knew they could hammer. And then they hammered that location. So this is, if you know how the operating system works, how the memory is allocated, this is what you can do. And if you know how the hardware works, you can actually figure out which locations are vulnerable. And after fooling the operating system to allocate a page table entry in a vulnerable location, they were able to take over the system. And that's essentially what the app does if you can actually download that. And let me know if it works if you download it. Probably you don't want to do that, but up to you. So later, similar folks actually showed that you could accelerate these attacks with the GPU. So you know about GPUs now. GPUs actually are able to generate a lot of memory accesses at the same time, right? And these folks figured out that, oh, you could actually do this via a GPU because GPU is able to hammer memory much faster than a CPU. And that's how you can accelerate. And they actually built a very interesting attack. If you have a mobile system, you have an integrated GPU. That integrated GPU is not as powerful as a separate GPU, but it's still powerful. And they were able to use the WebGL interface and the programs to remotely escalate privilege. And you can read this if you're really interested. And later, similar and other folks showed that there's something called remote direct memory access. We talked about direct memory access today, right? In direct memory access, you can actually access one location in memory directly and store the data into physical memory or somewhere else. You could do that on a remote computer. So if you use this interface called remote direct memory access, it's a programming model actually, you can access the memory of some other machine. And if you know what's going on, you can actually launch Rollhammer on that machine through the remote direct memory access. So you're sitting in this machine, and there's some other machine that you can have remote direct memory access to. By sending remote direct memory access commands to that machine, you hammer the memory in that machine, and you take over that machine remotely without having any physical access to that machine, without having that machine to install an app that you need. And these folks also did something very similar at the same time, and you can see the imagination. That must be based on some interesting thing. Okay, anyway, so this may be another security implication if you have unreliable hardware. Okay, so if you're curious, I mean, this is our first work that talked about this, and I'd like to point out a couple of things over here. These three students, Ross, Jeremy, and Jihe, they were actually undergraduate students who did research with us to work on this and discover this. And if you're really, really curious, this is actually the most up-to-date work on Rollhammer that talks about like what has happened since. In the last 5 years, where are we? in terms of both attacks and solutions and many, many other things. So if you're interested, you can take a look at that. So let me go back to virtual memory. So I think this is a very good place to tie back some of the fundamental things that we talked about, because we didn't know about virtual memory at the beginning of this course, but now we've built up a lot, and we know about virtual memory. But basically, the takeaway, I think, at this point is, if the hardware is unreliable, you can build all kinds of security mechanisms and protection mechanisms, like we've done in virtual memory, but you may be compromised. Virtual memory is a very good thing, but it assumes, it has a critical assumption. The hardware is really reliable. So my takeaway from this is the root of security and trust is actually at the very, very low levels. If you want security and trust and isolation, you really need to build it at the very low levels. And in this case, the low level means your hardware needs to be reliable and secure and trustworthy. And I've given the example of Rowhammer because that's something we've discovered and we've been working on for some time. But other people who worked on Rowhammer actually later went on to discover Spectre and Meltdown, which you may know of. How many people know of Spectre and Meltdown now? Okay, great. So that's another example where the root of security is really in hardware, right? Spectre is basically exploiting speculative execution and the site and the caches at the same time, because you're able to do speculative execution, and because you have caches, you bring in data into the caches in the wrong path whenever you mispredict the branch that you can later infer, and that data may be critical. Even though you may not have no access protection, access permissions to that data, you can infer what that data is. Meltdown is actually very interesting because it's also related to the virtual memory subsystem. It happens because some of the access protection checks are delayed because of speculative execution. And it's related to something that I'm going to very briefly touch on in a couple of slides. Basically, because of the delay in the access protection check, again, you can bring in data into the cache that you're not supposed to bring because you're speculatively executing. And then later, someone can infer the value of that data. And that value may be a really critical key, for example, encryption key or password. And because the hardware is not reliable, in this case, is not secure, it's not giving you the right security guarantees, you're exposed to this problem. And these are not easy problems. Actually, Spectre is a very hard problem to solve because, as you've seen, speculative execution, branch prediction, caches, they're all extremely important, right, for performance. One way of solving the problem is getting rid of all of that. But that's not a good solution, clearly. So how do you actually solve Spectre is an existing research problem. Okay, so basically there's some food for thought for you here before we return to virtual memory. What should we assume the hardware provides? That's a good question. How do we keep the hardware reliable such that we don't run into issues like this? How do you design secure hardware? And how do you design, actually, maybe secure hardware design is not that interesting because actually it's easy to design secure hardware. But it's very hard to design secure hardware with high performance, high energy efficiency, low cost, and convenient programming, all at the same time. And that's what you need for real architecture, actually. If you care about only security, you can design secure hardware, but it may not be used by anyone else in the world other than you, or very specific cases. But this is the real question at the bottom. Okay, so there's plenty of exciting and highly relevant research questions. And if you're interested, send me an email. Okay, let me go back to virtual memory, and we're going to close the lecture. So we've actually covered some issues in virtual memory. Virtual memory has a lot of other issues. But there are three major issues in virtual memory. How large is the page table, and how do we store and access it? I've given you the hint that the page table needs to be hierarchical. And you read chapter 8.4 and the backup slides if you want to know more about that. The second is, how can we speed up address translation and access control check? We talked about that. TLBs are a good way to go over here. The third one is actually even more intricate, and you really need to know architecture to be able to understand this well. I'm going to give you the problem very quickly. But basically, so we talked about address translation hierarchy and address translation and the cache hierarchy. How do these interact with each other? When do you do the translation in relation to the cache access? And that turns out to be an interesting question to ask today, because translation is limiting performance. And there are many other issues that we will not, actually, we didn't cover all of these issues also, but what happens on a context switch? How can you handle multiple page sizes? we're not going to cover. But let me give you a teaser for the third issue over here. Basically, the third issue is when do you do the address translation? And this is actually an important question, and I think this needs to be re-examined completely in today's systems for the reasons that I'm going to talk about in the last slide. So one question is, do you do it before you access the L1 cache, or do you do it after you access the L1 cache? You may think this is a simple question, but actually causes a lot of headache in the system. So basically, in other words, is the cache, L1 cache, virtually addressed or physically addressed? Now, there's a distinction between virtual cache versus physical cache. If it's physically addressed, you don't have any problems, because you've done the translation and everybody goes through that translation. But if you access the cache without doing the translation, you run into issues. So what are the issues? One issue is the synonym problem. Basically, two different virtual addresses can map to the same physical address, which means that same physical address can be potentially present in multiple locations of the cache. Why? Because you saw the example where we shared pages between two different processes, right? They have two different virtual addresses, they map to the same physical address. And if you access your cache with a virtual address, they will bring data into two different locations in the cache because you're using the virtual address to index the cache. Now, you have the same physical data replicated in different locations in the cache. What if you write to one of them? Now you have a coherence problem inside your cache, right? Within your cache, you need to keep these different copies coherent. And this causes a headache. So, okay, there are three ways of designing, actually, caches and virtual memory. So this is, you first do the address translation, and then you access your L1 cache. You don't run into synonym problems here. It's a physical cache, but clearly there's a downside. Your TL.B access is on the critical path, meaning that you have to do this access first, and then do this access. There's at least one cycle associated that you waste. And we know that this is really critical for pipeline performance, right? We designed the L1 cache so that you can quickly get data into the pipeline. Now we're adding this TL.B over here. I don't think so, right? That basically gets back, it takes a step backward. So the other option is having a completely virtual cache. After you access the cache, you do the translation. Or while you're accessing the cache, you do the translation, but the cache access is not affected by the translation at all. Now the problem here is the synonym problem. There's actually another problem called homonym problem that I'm not going to go into. It's in the backup slides. If you're really interested, you can take a look at it. But if you do this, then you have a lot of headaches to solve, like the synonym problem. So most systems today actually do something like this, virtual physical cache. What does this mean? This means that you do the translation in parallel with the cache access, but the stuff you store in the cache, the tags in the cache, is actually physical. So you don't have virtual tags in the cache. So the tag in the cache is not based on virtual address, it's based on physical address. And it turns out this solves the problems, assuming some conditions that we're not going to go into. But most systems actually do this, so that they don't put the TL.B access on the critical path, or they don't run into these horrible headaches with multiple virtual addresses mapping to the same virtual address mapping to different physical address, the same virtual address, different virtual address mapping to the same physical address. Okay, so let me summarize. Basically, we've covered virtual memory. It gives you the illusion of infinite capacity. A subset of the virtual pages are located in physical memory, and a page table maps virtual pages to physical pages. And a TL.B speeds up the address translation, and multi-level page tables keep the page table size in check. And we can do virtual memory protection on top of this. This is actually one of the most successful examples of architectural support for programmers, how to partition work between hardware and software, hardware-software cooperation, and programmer-architect trade-off. I've already discussed this. But going forward, actually, this is causing problems, actually. How does virtual memory scale into the future? There are three key trends. We have actually huge physical memory sizes today. Some of them obviate the need for this virtual memory. At least the translation may go away in some cases. But protection is, of course, a different question, right? You need protection somehow. So this is actually changing the landscape, especially with large memories, not just DRAM, but people are actually looking into new memory technologies. Have you ever heard of 3D X-Point? Intel's 3D X-Point? Maybe they call it something else, persistent memory now. It's actually a huge memory with phase change memory technology that can be very fast as DRAM. So this is actually being interesting. And physical memory systems are becoming more sophisticated. You don't have just DRAM, you have different types of DRAM and non-volatile memory, flash. They could all be part of your physical memory. And there are many accelerators also in the system that are addressing physical memory. It's not just the CPU. We were very CPU-centric. What happens if the GPU is also accessing physical memory? What happens if your AI accelerator is also accessing physical memory? What happens if your video accelerator is also accessing physical memory? Your speech recognition accelerator, all of these accelerators accessing physical memory. Your in-memory processing engine accessing physical memory. They all need to have some interface to access. And if you want to scale virtual memory to that level, to the sizes as well as to different accelerators, then you really need to think out of the box. So that's why people are actually having problems with virtual memory today. But it's such an important part of the systems that we design today. So hopefully you've enjoyed it. Anyway, have a good weekend. See you next week.